Hello students, today we will start with the magnetostatics. The source of magnetostatic is the DC current. When we talk about the analogy of electric field and magnetic field, so static electric field has the unit of volt per meter, and static magnetic field has unit of ampere per meter, and the unit of flux density, electric flux density, it is coulomb per meter square, and the unit of magnetic flux density, it is Weber per meter square. So D is equal to epsilon into E, but B is equal to mu into H, and the electric flux, it can be written as double integration D vector dot ds vector, and magnetic flux can be written as psi m, it is equal to double integration B vector dot ds vector. The unit of electric flux is coulomb, but the unit of magnetic flux is Weber. Okay, so now let me study about the Biot-Savart law. Biot-Savart law states that the differential magnetic field intensity dH produced at a point P by the differential current element ideal is proportional to the product ideal and sine of angle alpha between element and the line joining point P to the element, and it is inversely proportional to the square of the distance r between the point P and the element. So mathematically we define this is the current carrying wire I, and at point P we have to calculate the magnetic field intensity, and the angle is alpha. So mod of dH, it is proportional to ideal sine alpha, and the mod of dH, it is inversely proportional to 1 over r square. So mod of dH, it is proportional to ideal sine alpha by r square. So mod of dH, when we remove proportionality, then constant appears here. Then constant is 1 over 4 pi. So mod of dH, it is equal to ideal sine alpha by 4 pi r square. This is the magnitude format. And in the vector format, dH vector, it is ideal vector cross AR vector by 4 pi r square. This is the vector form, where AR vector is the location vector, which can be calculated by final minus initial divided by magnitude. As an example, the derivation for the infinite long current carrying wire. So we have to calculate the magnetic field intensity due to infinite long current carrying wire. Now we are assuming that infinite current carrying wire is placed along the z-axis, and at point P we have to calculate the magnetic field intensity. So the location of point P is at the bottom of the cylinder, and we are assuming the point P is rho phi 0, and the current carrying element, it is ideal vector, it is I dz az vector, and it is ideal vector. So we can solve the distance between this current carrying element and point P. It is under root of rho square plus z square, and AR vector is final minus initial by magnitude. So it is rho arrow minus z az by under root of rho square plus z square. According to Biot-Savart law, the DH vector is ideal vector cross AR vector by 4 pi r square. So ideal vector is I dz az vector because current carrying element is placed along z axis. A cross product with rho arrow minus z az by under root of rho square plus z square. So when we cross product this I dz az vector with rho arrow minus z az by under root of rho square plus z square, so az cross arrow, it is fi. So I dz and rho fi, az cross az is 0. So I dz by 4 pi rho square plus z square to the power of 3 by 2 rho fi. So total magnetic field H vector, it is equal to integration of dH vector, and it is I dz rho fi by 4 pi rho square plus z square to the power of 3 by 2, and it is equal to I upon 4 pi a phi and integration minus infinity to infinity rho dz upon rho square plus z square to the power of 3 by 2. So now we are putting z is equal to rho tan theta to solve this integration. So dz is equal to rho sec square theta d theta. And when z is minus infinity, then theta is minus of 90 degree. And when z is plus infinity, theta is plus 90 degree. So H vector is I upon 4 pi a phi minus 90 degree to plus 90 degree rho square sec square theta d theta upon rho square plus rho square tan square theta to the power of 3 by 2. So I upon 4 pi a phi vector cross product with 1 over rho minus 90 degree to plus 90 degree sec square theta over sec cube theta d theta. So 1 over sec theta, it is cos theta. When we solve it, then this answer comes as I upon 4 pi rho a phi sin theta, and the limit is minus 90 degree to plus 90 degree. So sin 90 minus sin of minus 90 degree. Then this value comes as 2. Sin 90 is 1. 1 minus minus of 1, it is 2. So this answer comes as H is equal to I upon 2 pi rho and a phi vector. So this is very important formula of magnetic field intensity due to infinite current carrying wire. Now let me solve one question regarding it. Infinite wire is placed along z axis and it carries current of 10 ampere in z direction. Then calculate magnetic field intensity at point 3, 6, 12. Then this is a z axis and the current carrying wire is placed along z axis. Okay, so the point P where we have to calculate the magnetic field, it is 3, 6, 12. So initial point, this point is will behave as a final point, and the initial point will be 0, 0, 12. So the value of rho, it is under root of 3 square plus 6 square. It is equal to under root of 9 plus 36. and rho is equal to under root of 45, and the magnetic field intensity H is equal to I upon 2 pi rho A phi. So I is 10 upon 2 into 3.14, rho value is root of 45 and direction is A phi. A phi vector can also be calculated by using ideal vector cross AR vector in the Cartesian coordinate system. So ideal vector is AZ vector because current carrying wire is placed along Z axis, and AR vector can be calculated final minus initial by magnitude. So it is 3 minus 0 AX plus 6 minus 0 AY plus 12 minus 12. It will be 0. So this AR vector is 3AX plus 6 AY by under root of 3 square plus 6 square. So A phi vector, it is AZ cross AX, it is A phi. So it is 3 AY vector minus 6 AX vector by root 45. So this answer comes as 0.23 3 AY minus 6 AX by root 45. Okay, so next question is infinite current carrying wire is placed along x-axis having current of 5 ampere in the x direction. Then calculate magnetic field intensity at point 6 minus 25. So we have to calculate the magnetic field intensity at 6 minus 25, and the initial point will be 600, and the distance between this point and the point is rho. So rho is under root of 2 square plus 5 square, and rho is root of 29, and AR vector is the same, final minus initial by magnitude. So it is minus 2 AY plus 5 AZ by under root of 2 square plus 5 square. So H vector, it is I by 2 pi rho, direction A phi. I is 5 2 pi, and rho is under root of 29 and A phi direction. A phi is the direction of H vector, which we can also calculate ideal vector cross AR vector. So this can be calculated by ideal vector is AX vector cross product with AR vector. AR vector is minus of 2 AY plus 5 AZ by root of 29. So this we can solve, and we can get the value of A phi. This is the value of A phi vector, which is the direction of magnetic field vector. So H vector will be 0.14 minus of 2 AZ minus of 5 AY plus root of 29. So the next topic is calculate magnetic field intensity due to finite length current carrying element. Now we initially we calculated due to infinite length, and now we are trying to calculate the magnetic field intensity due to finite length. So this is a finite length current carrying wire where DL vector, ideal vector is I dz az vector. Okay, and this is the point where we have to calculate the magnetic field intensity. This point is rho phi 0, and this is the initial point, which is 0 phi z. Okay, so AR vector we can calculate final minus initial by magnitude, rho arrow minus z az by under root rho square plus z square. So DH vector is ideal vector cross AR vector by 4 pi r square. So it is I dz az vector by 4 pi r square. R square is rho square plus z square. AR vector is rho arrow minus z az by under root of rho square plus z square. So simply we will cross product with AZ cross arrow. AZ cross arrow is A phi, and AZ cross AZ is 0. So I dz, it is rho A phi upon 4 pi rho square plus z square to the power of 3 by 2. So the total magnetic field H it is equal to integration of dh, so I upon 4 pi a phi, limit z1 to z2, it is rho dz upon rho square plus z square to the power of 3 by 2. So z is equal to rho tan alpha, so dz is equal to rho sec square alpha d alpha. When z is equal to z1, alpha is alpha 1. When z is equal to z2, alpha is alpha 2. So h vector, it is I by 4 pi a phi alpha 1 to alpha 2 rho into dz. Dz is rho sec square alpha d alpha upon rho square plus rho square tan square alpha to the power of 3 by 2. So it is I by 4 pi rho a phi alpha 1 to alpha 2 sec square alpha upon sec cube alpha. So 1 upon sec alpha, it is cos alpha. The integration of cos alpha, it is sin alpha. So the answer for magnetic field intensity, it is I by 4 pi rho sin of alpha 2 minus sin of alpha 1, and direction is a phi. A phi is the magnetic field direction. So I by 4 pi rho sin alpha 2 minus sin alpha 1 a phi. This is very important result for finite length. When the length is infinite, so again result will come I by 2 pi rho a phi vector. So now there is one simple numerical. We want to calculate the magnetic field intensity to finite length wire of length a placed along y-axis at point a by 2 comma a by 2. It carries current I in the y direction. So this is the diagram where current is flown in the y direction, and at a by 2 comma a by 2 we have to calculate the magnetic field. So alpha 1 angle is minus of 45 degree and alpha 2 angle is plus of 45 degree. Here we are observing this is the length a by 2. So AR vector is AX vector. When we join this vector, so this is AX vector. So the formula for finite length current carrying element, it is I by 4 pi rho sin alpha 2 minus sin alpha 1 a phi vector. So I by 4 pi into the value of rho, it is a by 2 sin 45 minus of 45 a phi vector. So simply we can solve I by 2 pi a sin 45 is 1 by root 2 minus sin of minus 45 is again minus of 1 by root 2, so it will be plus 1 by root 2. So this answer is I by root 2 pi a, and the direction is a phi. So a phi direction, again we can calculate, it is ideal vector cross ay vector. Ideal vector is ay because current carrying element is kept in the y direction, and AR vector is AX. So AY cross AX, it is minus of AZ. So we can get here the value of H vector, it is I by root 2 pi a and minus of AZ vector. Next question is, given a square loop having side length a, then find the magnetic field intensity at the center. So this is given a square loop in which current is flowing in the clockwise direction, and at the center we have to calculate the magnetic field intensity. So it's very simple question because due to one wire we already calculated the magnetic field intensity, which is I by root 2 pi a, direction is minus of AZ. So there are four such wires. So simply we will multiply with the 4, and answer is 4 I by root 2 pi a, direction is minus of AZ. Due to each and every wire, the direction of magnetic field is minus of AZ. As we can see here, due to the second segment, this is the second segment, suppose this is first segment, this is third, and this is the fourth segment. So due to the second segment, ideal vector cross AR vector, ideal vector is in X direction, so AX cross AR vector it is in minus of ay, so again direction will come as minus of az. For the third segment, ideal vector is minus of ay because current is going in the downward direction here, and ar vector is minus of ax, so again direction will come as minus of az. So by using this rule, we can get this answer 4I by root 2 pi a minus of az. Next question is, a circular ring of radius a carries a current I in the phi direction. Phi direction is the anti-clockwise direction. Calculate magnetic field intensity at point P at height h above the center of the ring. So this is the ring given, and current is flowing in the anti-clockwise direction in this direction. In this direction current is flowing. Okay, so ideal vector, it is I a d phi phi vector. We can get here a small segment ideal vector, and ideal vector is I a d phi phi vector, and the coordinates of this point is a phi 0, and this will be the initial point here, and at the height h, from this point, so it is 0 phi h. We have to calculate the magnetic field intensity. Okay, so we can get the value of AR vector. It is rho arrow minus z az by under root of rho square plus z square. Okay, and the dh vector, according to Biot-Savart law, dh vector is ideal vector cross AR vector by 4 pi r square. So it is I dz az vector cross AR vector. AR vector is rho arrow minus, okay, once let me check here. Okay, so ideal vector is I a d phi a phi vector cross product with AR vector. AR vector is minus a arrow plus h az by under root of a square plus h square, and we will simply cross product it. So when we cross product it, so I a d phi a phi cross arrow, it is az, and a phi cross az, it is arrow. So we'll just put here I a d phi upon 4 pi a square plus h square to the power of 3 by 2 and a z plus h arrow. Due to symmetry, rho term will cancel here, because when we resolve this magnetic field, then this rho term will cancel each other. Only z term will present here. So due to symmetry, rho term will cancel. So total magnetic field, it is h vector. It is integration of dh vector, and h vector, it is I a square az vector upon 4 pi a square plus h square to the power of 3 by 2. It is 0 to 2 pi d phi. So this term 2 pi and 4 pi will cancel, and the answer is I into a square az upon 2 a square plus h square to the power of 3 by 2, and this is our required answer. So exactly at the center, what is the magnetic field? Exactly at the center, h will be equal to 0, and when h is equal to 0, so answer is I by 2a, and the direction is az. So the magnetic field will look like this. Magnetic field always creates the closed path, so magnetic field is looking like this, and in this way. here the question is given a circular loop x square plus y square is equal to 9 and z is equal to 0, carries a DC current of 10 ampere in plus Fi direction. Determine H vector at 0, 0, 4 and 0, 0, minus 4. So we have to calculate at H vector at 0, 0, 4 and 0, 0, minus 4, and the value of H vector, it is IA square AZ upon 2A square plus H square to the power of 3 by 2. So current is 10, A square, it is 9 because the radius is given 3 upon 2 A square plus H square to the power of 3 by 2. So we'll just put here 2 into 9 plus 16 to the power of 3 by 2. So the value of H vector, it is 0.36 AZ. So at 0, 0, 4 and 0, 0, minus 4, answer will be same because for both current direction is same. Now we study about the Ampere's law. Ampere's law states that the line integral of H around the closed path is equal to the current enclosed by that path. So according mathematically, the line integration of H around the closed path, it is circulation of H. So it is H vector dot dl vector. It is equal to current enclosed by that path. This is Ampere's law, or this is also called as Ampere's circuit law. When we apply the Stokes theorem here, then it is double integration del cross H dot ds, and current enclosed is double integration J vector dot ds vector. So when we compare, it is del cross H is equal to J. So this is Maxwell's equation derived from static magnetic field from Ampere's law. Here we are getting circulation of H vector is not equal to 0. So we conclude that magnetostatic field is not conservative, as del cross H is not equal to 0 and del cross H is equal to J, and it is also rotational. So the question is, given a solid wire of radius A carries current I in the Z direction, calculate magnetic field intensity inside and outside the wire. So this is the question given. This is a solid wire which has radius is equal to A, which is solid. So we have to calculate inside magnetic field and outside magnetic field. So the cross sectional area is pi a square. In the pi a square, current is I. In the unit area, current is I by pi a square. So in the pi r square area, current will be I by pi a square into pi r square. So pi and pi will cancel. So current enclosed is equal to I r square by a square. Case number 1 is inside wire r less than a. So for r less than a, current enclosed is I r square by a square. So we'll simply put here. So h into 2 pi r is equal to I r square by a square. So this answer is I r by 2 pi a square a phi. For r greater than a, which is outside the wire, circulation of H vector dot dl vector, it is equal to I enclosed. So h into 2 pi r, it is equal to I. So h is equal to I by 2 pi r a phi. So this will be the graph. Inside it is a linear wiring and outside it is a decaying graph. we start with magnetostatic. Source is DC current, and what is the analogy for static electric field and magnetic field? So for the static electric field, electric field intensity is defined as E vector, which is volt per meter, and here magnetic field intensity is in ampere per meter. Here D, which is electric flux density, it is coulomb per meter square. And here is B. B is magnetic flux density, it is in Weber per meter square. It is also called as Tesla. So T is equal to epsilon into E, and B is equal to mu into H. Electric flux. Electric flux is psi, it is equal to double integration d vector dot ds vector, and magnetic flux, it is psi m, it is b vector dot ds vector. So it is coulomb, it is measured in coulomb, and this is measured in Weber. Biot-Savart law. Let me study Biot-Savart law. It states that differential magnetic field intensity dH produced at a point P by the differential current element ideal is proportional to the product ideal and sine of angle alpha between the element and the line joining point P to the element, and it is inversely proportional to the square of the distance r between point P and the element. So mathematically, how we define the Biot-Savart law? This is the current carrying wire in which current I is flowing, and this is a small segment ideal which is making angle alpha with the line joining this element with the point. So the mod of dH, it is proportional to ideal sine alpha and it is inversely proportional to r square. So when we combine these two, it is mod of dH, it is proportional to ideal sine alpha by r square. Okay, so when we remove this proportionality, then constant comes here, and that constant is 1 by 4 pi. So this is the magnitude form, and what is the vector form of Biot-Savart law? It is ideal vector cross AR vector by 4 pi r square. Okay, so this is the vector form. Okay, and AR vector is final minus initial by magnitude. Question is, calculate magnetic field intensity due to infinite long current carrying wire. So there is one infinite current carrying wire which is carrying current I, and at point P, which is present at the bottom of the cylinder, and it is rho phi 0. At this point we have to calculate magnetic field intensity. So the perpendicular distance is rho and the height is z. So here I dz as it is ideal vector. So AR vector is rho arrow minus z az by under root of rho square plus z square. This is AR vector. So what we will do, according to Biot-Savart law, it is ideal vector cross AR vector by 4 pi r square. So this is I dz az vector cross AR vector. AR vector is rho arrow minus z az by under root of rho square plus z square by 4 pi rho square plus z square. R square is rho square plus z square. So when we cross product is az cross arrow, it is a phi, and az cross az it is 0. So total magnetic field H vector, it is integration dH vector, and it is I dz into rho fi by 4 pi rho square plus z square to the power of 3 by 2. So it is I by I into fi by 4 pi and integration minus infinity to infinity rho dz upon rho square plus z square to the power of 3 by 2. So to solve this integration, z is equal to rho tan theta, where dz when dz is equal to rho sec square theta d theta. When z is minus infinity, theta is minus of 90. When z is plus infinity, theta is plus 90. So h vector, it is I by 4 pi fi minus 90 to plus 90 rho square sec square theta d theta upon rho square plus rho square tan square theta to the power of 3 by 2. So h vector, it is I by 4 pi fi 1 over rho minus 90 to plus 90 sec square theta upon sec cube theta. 1 plus tan square theta is sec square theta, and sec square theta to the power of 3 by 2, it is sec cube theta. So it is 1 over sec theta, it is cos theta, and I by 4 pi rho a phi, the integration of cos theta, it is sin theta. So h vector, it is I by 4 pi rho sin 90 minus sin of minus 90. So it is 2. So so h vector, it is I by 2 pi rho a phi vector. Next is a infinite wire is placed it carries current of 10 ampere in the z direction. Calculate magnetic field intensity at point 3, 6, so we have to calculate the magnetic field intensity at 3, 6, 12, and the initial point will be 0, 0, 12. This is the final point. The perpendicular distance between these two, it is rho. So rho it is equal to under root of 3 square plus 6 square. It is under root of 9 plus 36. So rho is equal to under root of 45. So h vector, it is equal to I by 2 pi rho. Direction is a phi. So h vector, it is 10 upon 2 into 3.14 into under root of 45, and the direction is a phi. Direction a phi, it is equal to ideal vector cross AR vector. So a phi vector, it is AZ vector cross 3ax plus 6ay by under root of 9 plus 36. So a phi vector, it is 3ay minus 6ax by root of 45. So AR vector is, so we'll put here, so I by 2 pi rho, it is 10 by 2 into 3.14 into root of 45. This answer comes as 0.23. So we'll put here 0.23, and the vector. This is the vector. So vector is 3ay minus 6x by root of 45. So this is our desired answer for the magnetic field. An infinite current carrying wire is placed along x-axis having current of 5 ampere in the plus x direction. Calculate magnetic field intensity at point 6 minus 2 5. So this wire is placed along x-axis and we have to calculate the magnetic field at 6 minus 2 5. So the initial point on the x-axis will be y and z is 0 0 always, and we will keep here x is equal to 6. So rho is equal to under root of 2 square plus 5 square, and rho is equal to under root of 29, and AR vector is minus 2 AY plus 5 AZ by under root of 2 square plus 5 square. So IH is equal to I by 2 pi rho A phi. It is 5 by 5 by 2 pi. Pi is 3.14 into rho. It is root of 29 A phi vector. So A phi vector is direction of H vector. It is ideal vector cross AR vector. Ideal vector is AX vector, and AR vector, it is minus of 2 AY plus 5 AZ upon under root of 2 square plus 5 square. So this answer comes as minus of 2 AZ plus 5 minus of AY by root of 29. So this is the answer for H vector, magnetic field vector. It is 0.14 minus of 2 AZ minus of 5 AY by root of 29. Calculate magnetic field intensity due to finite length current carrying element. So this is the finite length current carrying element, and at point P we have to calculate the magnetic field. It is rho phi 0. This is the point, and AR vector is rho arrow minus Z AZ by under root of rho square plus Z square. So according to Biot-Savart law, DH vector, it is ideal vector cross AR vector by 4 pi R square. It is I dz AZ vector by 4 pi R square. R square is rho square plus Z square. So DH vector is ideal vector cross AR vector by 4 pi R square. So it is I dz AZ vector divided by 4 pi R square. R square is rho square plus z square, and AR vector is rho arrow minus z az by under root of rho square plus z square. So dh vector is I dz az cross arrow, it is fi, az cross az is 0, so I dz upon I dz into rho fi by 4 pi rho square plus z square to the power of 3 by 2. So total magnetic field H, it is equal to integration of dH, so I by 4 pi Fi, z is equal to z1 to z2, we will integrate it, it is rho dz upon rho square plus z square to the power of 3 by 2. So to solve this integration, we will put z is equal to rho tan alpha here. So dz is equal to rho sec square alpha d alpha. When z is equal to z1, from the figure we can observe alpha is equal to alpha 1. When z is equal to z2, then alpha is equal to alpha 2. So h is equal to I by 4 pi a phi alpha 1 to alpha 2. It is rho into rho sec square alpha d alpha upon rho square plus rho square tan square alpha to the power of 3 by 2. So it is I by 4 pi rho sec square alpha upon 1 plus tan square alpha, it is sec square alpha, and sec square alpha to the power of 3 by 2, it is sec cube alpha. So 1 by sec alpha, it is cos alpha. So when we integrate it, so it is sin alpha. So I upon 4 pi rho sin alpha 2 minus sin alpha 1, and direction is a phi. So this is the magnetic field intensity due to finite length current carrying wire, and this expression is very important for GATE exam. So it is I by 4 pi rho sin alpha 2 minus sin alpha 1 and a phi. So calculate magnetic field intensity due to finite length wire of length A placed along y-axis at point a by 2 comma a by 2. It carries current I in y direction. So this is carrying current I in y direction, and here we are getting alpha 1 is minus 45 and alpha 2 is plus 45. So H vector, it is I by 4 pi rho sin alpha 2 minus sin alpha 1 a phi. So it is I by 4 pi into a by 2 sin 45 minus sin of minus of 45 a phi. So it is I by 2 pi a 1 by root 2 plus 1 by root 2 a phi. So it is 2 by root 2. So it is I by root 2 pi a phi. This is H vector. And what is a phi vector? It is ideal vector cross AR vector. Ideal vector is AY and AR is AX. AY cross AX, it is minus of AZ. So H vector, it is I by root 2 pi a minus of AZ.